Okay, so tell me your very first step on number 18. All right, my people are picking up papers. Okay, this is number 18 on the unit review. Tell me your first step. It's always the first step. VCE. Okay, so tell me what the VCE is. It says a student places blah 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 iron nail and blah 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 copper 2 sulfate. During the reaction, the iron is oxidized to iron 3 as the copper is replaced. VCE. FE. Ooh. Hold on, I gotta get that fancy pen. Okay. FE. They cross, right? Because 2 and 2 cross. I heard FeSO4,
Yeah.
but you gotta read. It says F iron 3 is what it's oxidized to, the what it reacts to, so it's iron 3 sulfate. Fe2 SO4 3. A little bit more complicated, right? And copper. All right, so it's coming back to us. We're like, yeah, I can do balance chemical equation. Not balance though. Balance. 3 here. Okay. 2 in front of the iron and 3 in front of copper. Woo, done. Okay, so what does this look like for reaction? You put some iron filings in. What color is this substance? How do you know? Copper 2 is blue, right? And then you make this random thing. Looks like nothing. It's just probably maybe clearish, maybe a little greenish, and then copper solid. Did you do this reaction? Yeah, we did it in the types of reactions lab. Yeah. Okay, so a student places an 8-gram iron nail in this amount of this molarity during the reaction. What do you notice I'm giving you? I'm giving you information about reaction 1 and information about reaction 2. What did I tell you that was key in terms of like what kind of problem this is? What kind of problem is this? One of the dreaded limiting reagent ones, right? So I wanted to do this one because this one is a review of LR, and that's what a lot of you guys are asking about. Hey, do you have a question? Okay, you're going to help me. Thank you. So whenever I give you something about one reactant and then something about another reactant, that means it's an LR problem. So when you do your LR problems, first you're HBC, then you find your moles of both reactants. Okay, so here we go. You're hopefully writing this down because this is on the unit review. I'm doing one of the big ones for you. Okay, so 8 grams of iron. And it says iron nail, but it's just iron. What's the step here? No, this is just this one first. Sorry. I'm only starting with iron. So what's my next step? Go for Aiden. Get moles. What's that molar mass? PTOE. I think you're right. 5.85 grams. And everybody should be calculating with me. Just get your fingers back in practice mode. I know you're like, where's the numbers on the calculator? You forget over the weekend. I know what the decimal is. I know how to read the E number. Yeah. When you look at it and you're giving givens about reactant 1 and reactant 2. If it doesn't say iron is reacted with excess hydrochloric acid, so the word excess actually indicates to us that that one is excess, the other one is LR. In this case, it's giving us 2 quantities, and we don't know who the LR is. So we have to figure out who the LR is first before we can approach the problem. Okay, so how many moles is this? 1, 4, 3, 2. I'm stopping there. Moles of iron. And what do we label this? This is how much we have of iron, right? Don't forget to try to keep it organized so you can find your information. Okay, now we have to consider the next reactant. And how do we consider that? That says 150, by the way. How do we do this one to get moles? Hey, together now. That's when you do the times thing. Maybe we do the times thing every. Okay, so this big M means moles over liters. So what do I need to do to 150 milliliters first? So 0.150 liters. All it does back to the decimal at 3 spaces times 1.2, and this molarity big M is moles of copper 2 sulfate per 1 liter of that solution. So that liter and liter cancels. So 0.15 times 1.2 is 0.18. 0.18 moles of copper 2 sulfate. Again, that is how much I have. Okay, so I'm just going to box those off so I can find them easily on my crowded work paper. Alright, so I've gotten to have of both. What's next, guys? How much you need of the other one using the mole ratios. So, how much do I need? What's the ratio that copper 2 sulfate reacts with iron? So 3 moles of copper 2 sulfate react with 2 moles of iron according to the BCE. So I need that times 3 halves. So 0.2148 moles of copper 2 sulfate. And that's how much I need. Whew. What's my problem here, guys? I need 0.2, I only have 0.18, right? So what's the problem? It's going to run out. It's the limiting. So once we figure that out, we are done with finding the LR. So I'm going to put, who was it? Copper 2 sulfate. Put a little LR above that so you don't forget, because you work so hard. And then what are you putting above this one? Excess, to remind yourself that's the excess reagent. Okay, so we just did that to figure out what your LR was. Now let's kind of finish reading the problem. During the reaction, the iron is oxidized. Okay, we read that. After the reaction, the mixture is filtered, meaning the liquid solid stuff's poured through the filter paper. The mass of the filter paper is 97 grams. What should the mass of the filter paper be after the mixture is filtered and dried? So it sounds kind of technical, right? But what are they really asking for? What's the real question? So what are we looking for? Mass of solid plus the filter paper. So what solid are we looking for? The copper made, right? So we're going to figure out how much solid copper is made. So the question is grams of copper made. But who do you start with? The moles that you have of the LR, right? So you're starting with this. Let's bring that down here, and we're going to go. So the real question is grams of copper made. And so that copper made is going to get caught in the filter paper, but we very well could have excess iron left over as well. Iron is a solid, right? It could be still in this, there, it definitely is. So we're probably going to add that mass left over too. So this is kind of a big problem. It looks like a little problem, it's a big problem. So here let's go ahead and start with the copper first, and then we'll kind of backtrack to that second thought. So I'm starting with 0.18 moles of copper 2 sulfate. Okay, what's my next step? Who do I care? I'm in one thing, I need to get to another thing. Mole ratio, so I have copper 2 sulfate to copper ratio is 3 to 3, right? So 3 moles of copper for every 3 moles of copper 2 sulfate. Then 2 grams. So 1 mole of copper weighs 63.55 grams of copper. And that gives me the grams of copper remaining, or that was produced in this particular reaction. So, how much? 11.44. I'm just rounding up. Okay, so that's how much is made in the reaction. How much did the filter paper weigh? 0.97 grams for the filter paper. So that gives us 12.41 grams total. So that might be your initial instinct for your first part of your answer. And I can't remember if on the answer key, if I put just this or plus the iron. But I will note, we might have to figure out how much grams of excess iron. And once we figure that out, we could add that to that answer over there. And we would add that to get the final total precipitate that was remaining and that was made. So if we had to get that, we could. Let me go back up here and let's see where we need to go from here, though. Okay, so the student masses the filter paper after the reaction is complete and filtered and records the mass at 11.98. What is the percent yield? So what do we do for this one, just for what we have so far? So So we find the actual yield and theoretical yield. We actually already have them both. Okay, but who is the actual yield? I want you to tell me. Okay, because that's actually what's made in the lab. That's what the student made. Where's the theoretical yield? Right, because that's what we said they should have gotten after all this theoretical math in La La Land. That's on the board here. And so that's our theoretical yield. A lot of times you're going to have to I mean, you will always have to calculate theoretical yield. Sometimes you already do it and you're like, oh my gosh, I got to calculate it. No, you've already done it. So don't calculate it again. So actual yield over theoretical yield times 100 is our percent yield. And so let's see, is this person a good chemist? Right. Okay, so that many grams per that many grams. And remember, this is yield, so they're both in the same units, grams of product and filter paper, grams of product and filter paper. 90 what? 96% from 0.5. Well, I already wrote 96. All right, so they're pretty happy with themselves. Big chilling with their glasses on. Their goggles. These are goggles. Yeah. Okay. What? They're goggles. With that little. With that beaker and test tube. Those are teeth. I don't know. Okay. So, yay. Did we remember a little bit of LR? Okay. Problem set 12. Let me get one question right now, and then we'll start notes, and then we'll get some more at the end. First come, first serve. Hayden. You might have to read that to me. Come on. Yes, I got it. You need to, I think. Hold on. Consider the combustion of magnesium. That one? Yeah? Got it? Okay. All right. Are you guys considering the combustion of magnesium? You're considering it. I'm considering it. What's that BCE? All right. So you know to start with. Hold on. Mg. Combust means react with O2. And MgO. Okay. Do not put water and carbon dioxide here. I know all combustion. You're like, oh yeah, it makes carbon dioxide and water. Do you see any carbon? No. It cannot make carbon from no carbon. So do not get in the habit of going just combustion as CO2 and water. It's only for combustion of hydrocarbons, not metals. Okay, so this balance would be yay. Okay. Determine the limiting reactant if 7.24 moles of magnesium react with 3.86 moles of oxygen. What have I already done for you? I've gotten you to moles, right? Step 1 done. What's step 2? I hear you saying this is our half of both, just in case you didn't realize there's half of both. And you want to figure out how much you need of the others. So what's the ratio? What goes here? What? 1 mole of oxygen for every 2 moles of magnesium. And then vice versa, 2 moles of magnesium for every 1 mole of oxygen. Okay, you can do this in your head. What's that? 3.62 moles of oxygen. That's how much you need. And I'm actually going to go ahead and compare that to that. This is how much, remember, this is how much I have. So I got 3.86, only 3.62. I got excess oxygen. So let's just doubly confirm this one. How much do you need? What is that? 7.2 or 7.34? What is it? 7.2. 7. There you go. Moles of magnesium. Okay, so if you need 7.72, does that confirm our initial thought? Right, you need a lot more than you have. Not a lot, you need more than you have. So this one is your LR. So we know who our LR is. All right, and then how much magnesium oxide is formed? So we know who our LR is. How do we start part B? So you're taking the moles of magnesium you have, and you're starting part B with it. Okay, so the question for part B was how much magnesium oxide is formed. That's our question. So 7.24 moles of magnesium. Tell me what I do from there. Any mole ratio, which is what in this case? 2 to 2. So 2 moles of magnesium oxide form for every 2 moles of magnesium. Last step. Convert to grams. What's that molar mass? Say again.
40.31.
4.31 grams. Answer. Okay. How much?
291.
I think that's really large.
That's 2.
I'm just checking myself here. 292, yeah, 292-ish grams. Okay, and then last one, determine the percent yield if 288 grams of magnesium oxide was collected. If 288 grams was collected, what yield is that? Actual yield of magnesium oxide collected. And then this is theoretical yield, so 292. And were they a good chemist? Oops, sorry, times 100. What was their yield? 98, so they're almost perfect. Or 99, actually, right? 98.6, okay. Whew. Perfect. Woo! Okay, who's next? We'll draw somebody with hair like that. Lab coat. I have a big chin. Okay. I can draw now. I used to draw Barney. I'm not going to draw Barney. He's got little hands. This is Barney. Actually, the lady dinosaur. He's got large, he's got little hands. I know, this much chemistry. Okay. Okay, so let's take a break from PS12 into this. Let's switch notes to notes, 15-ish minutes, because I didn't want to overkill it last week. And this is I think it's a pretty easy concept, but there are 2 terms we're going to be using a lot. Guess what the 2 terms are based off of your looking at the paper? Entropy and enthalpy. Everybody got this paper, yes? Okay. So let's roll. This part right here is the easy stuff. We have 3 things that can happen in a reaction. We put reactant 1 together with reactant 2. No, nothing happened. So what would be a situation where nothing would happen? When did we ever write NR, no reaction? Okay, so single replacement with less active metal, right? And also, no, I don't want an example. Just give me scenarios. There's also a double replacement with.
We don't like that.
Yeah, you can write this on paper. That's why I printed this for you. Okay, double replacement with all blank compounds. When did we cancel out every single ion and call it a spectator? When they're all, not all precipitates, they're all soluble, aqueous. Okay, so they're all aqueous or soluble. Okay, so that would be a scenario where everything was on the, soluble part of the solubility list. So everything's a spectator. So if they're all spectators, what's happening during the reaction? Nothing. They're all just watching each other, sit in the solution. Hey, what you doing this weekend? Nothing, because I'm a spectator right now. Okay, so these things make nothing happen. Generally, these things are not going to happen because of their whole activity, but also you can have things that there's not enough energy. So sometimes things need a little help. So if I just put some potassium chlorate on my counter and I sat it here, would it just decompose? No, it doesn't have enough energy. It doesn't have enough heat. So do you remember in some of our decomposition reactions, we said it required heat? That was where we put like arrow with a little triangle. That's a needed component. It's not a reactant, but it's a condition that is needed before this reaction can occur. So those are some things that won't happen until you give it enough energy or until you put it in the right conditions. Or things react. So what are some common evidences of chemical reaction? Okay, formation of pure liquids. I'm cool with that. Okay. Precipitation. gas evolution, color change. We've done this like a million times, right? Heat evolved, heat or cool, some sort of temperature change, things like that. And when they react, and we can feel it react, we can see it react. And then some things can react only after you've given them enough energy. And that energy is called activation energy. Who's heard of activation energy? Okay, you heard about it in biology, right? What biomolecules? There's only 4 biomolecules. Which of the biomolecules speeds up chemical reactions by lowering the activation energy? Enzymes, which are the 4 types of biomolecules? Proteins. I heard it. Proteins. So the activation energy. So an example, something that you're really, really quite familiar with, are enzymes. And enzymes are catalysts. And catalysts, what did I just say they did? Okay, they speed up a reaction by lowering activation energy. EA is activation energy. That's how they work. So who has ever seen something, and I'm not sure I have this on your paper. This is not on your paper yet. Who's ever seen something like this? A graph like that? Maybe. And it's basically reactants going to products. And I can draw it the opposite way too. I can draw it like this. Reactants going to products. Sketch those on the back of your paper if you don't have space on the front. Give yourself a little sketch. And actually, I think I have more on the next slide. Let me just double check, because I probably have prettier pictures. No, you don't have to get everything, just some things. I don't have pretty pictures. I'll draw these a little bit better here. So these are called reaction coordinates. They're called reaction coordinate diagrams. And they actually give us a lot of information about what's happening during a chemical reaction. So if you're looking at reactants to products, and I'll tell you that this is energy, well, I'll call this temperature. Yeah, we'll call it temperature. T is temperature, that's on the y-axis. All right, so over the course, actually I'm gonna put E, because I want to call it energy. We'll talk about temperature in thermochem. I don't want to get into what temperature is in a second right now. So in terms of the coordination of the reaction, reactants have lower energy than products do. So if you're thinking about it, did energy go into the reaction or did energy come out of the reaction? If I went from point A to point B, it was put in, because how do you get reactants to a higher energy when they go to products? You put energy into that reaction. We call that kind of reaction an endothermic reaction. You've heard the term endothermic. The other one is exothermic, right? So endothermic is when the energy, sorry, this is in the way now, when energy goes into the reaction. So if reactants on this one start high and products end at low energy, energy was obviously exported out, released, emitted, whatever you want to say, right? So this would be an exothermic reaction because energy leaves or is released from the reaction. And so we actually have little symbols that actually indicate this whole endothermic and exothermic nature. And so the symbols are this energy from the reactants to the products. There's a difference there, and I'm just going to draw a line indicating that difference. So that's the energy difference. Do you see it? That is called delta H, and H stands for enthalpy. We're going to talk about that. And since the energy is going into the reaction, you're adding it too. So do you think that's a positive sign or a negative sign? Positive, right. So it's a positive energy. Delta H is positive. Opposite, the reactants are losing energy down to this state. So that you can see the difference in energy is about yay big. That delta H is, guess what, negative. Because it is losing energy. It's emitting. It's being subtracted from the reaction. So those delta H's that you just drew, those delta H's you just labeled, that's called enthalpy. Enthalpy of reaction. Okay, so why am I talking about this now, right after we just talked about activation energy? There's a hill here. You see the hill. It's really difficult sometimes to overcome that hill. And so that energy that, let me draw this here, the energy that the reactants have to put forth to get all the way up this hill is this right here, this straight blue line. That blue line is called activation energy, energy of activation. The energy that's required to get that reaction going. And that's quite a bit of energy to go up that hill. Catalysts, actually, their job is to lower that activation energy from this tall to this tall. And so that means that I can still get from reactants to products, but I don't have to go up the tall hill, I can go up a shorter hill. So I'm going to draw that as a dashed line. Isn't that a little bit more manageable? It's a little shorter hill. It's a lower activation energy. So I'm just going to put another black line right there to indicate that's a lower activation energy. And that pathway is allowed, that reaction is allowed because a catalyst is present. The red one, catalyst is not present. It's going to be difficult. The black one here, catalyst is present, so therefore it can be a shorter, a little bit more manageable activation energy. So how would this one look? Where would the hill be? With a catalyst. Okay, lower than this or lower than R? Starting in R, yeah, you have to start at the same spot, but you're just going to go up a little less and still go down to the same. So that activation energy is like, heck, look at that. It's like nothing. I can snap and it's that much energy. Okay? It's a little bit easier for that activation energy than the previous one where it was like that. So that's what a catalyst does. It speeds up chemical reaction because it can go over the hill faster. Can I go to the next slide?
Yeah.
Yeah? Okay. So this is actually what we just talked about. I'll start down here for enthalpy. Whenever we're talking about reactions actually happening versus not happening, there are two forces in the world that make reactions happen. One is the amount of energy, the enthalpy, that's related to that particular reaction, and one is entropy, which is a measure of disorder. So enthalpy, here it is right here, heat. So I was talking about heat energy, thermal energy, energy is exiting, energy is entering. That heat is the measure of potential and kinetic energy. PE is potential energy, KE is kinetic energy. I guess I'll let that as a blank. Yeah, okay. And so whenever we're trying to figure out which version of this is favored amongst the universe, so basically the universe is everything, right? And certain things happen in the universe because they please the universe. If energy is released to the universe, it makes us more stable. All reactions have lots and lots of energy. But if you think about you, if you have a lot of energy, you're hyped up on sugar and caffeine, you're just really unstable, and you're not going to make it that long. So you're really unstable, that means that that's a stressful environment. Chemicals are the same way. If they have a lot of pent-up energy inside of them, they're really stressed out too. So they prefer to release their energy, and they come to a happier, calmer, namaste place, okay? Just like we do. So when I said release energy, does that say endo or exothermic reactions? Exo, okay? So an exothermic reaction, so delta H is positive or negative, favors the reaction happening. That actually is going to happen. So if it's an endothermic reaction, it still could occur, but it's kind of not as likely to happen. Just like if you had to bake a cake, right? Is the cake going to bake itself? No. What do you have to do with it? You're going to put it in the oven. You've got to give it a little help. So that's why I said cake's not going to bake itself. It's not just going to happen. Things need to be a certain, they need help, or they need to be in a certain fashion for them to naturally occur. Entropy. So entropy is a measure of disorder. We all probably have our own definition of disorder. So disorder might be your room at home. Might be really not so great and tidy. Sometimes, like my room is a lot of disorder sometimes, but that's okay. The universe actually favors disorder. Because think of, okay, All these candies. All these candies. I have more candy in my car for you. I forgot about that today. I gotta get it. Okay, if they're all in their nice little orderly places, it takes a lot of energy to kind of keep that nice and orderly, right? It's really easy to just throw it in the basket. And it's yummy here that way too. But it takes a lot of energy to kind of keep it nice and organized. They're also touching each other, they're attracting, they're repelling, maybe they're like positives and negatives. Sometimes two negatives get together, they're repelling. That's kind of actually, that's just like really a lot of pent-up energy. This, ready? Don't hit anybody in the face. You get candy, and you get candy, and you get candy, and you get candy, and you get candy. Oh, and you get candy. Okay, there's more. I will get more. So that actually is a lot easier for a reaction to handle. The reaction doesn't want things all compacted together. It prefers it to be disordered. And that means entropy, a measure of disorder, is going to, you're going to favor the reaction when entropy increases. Okay, so I'm just going to erase it. When entropy increases, it favors a reaction happening. But how do you know, when you're looking at a piece of paper with a chemical equation on it, how do you know if the entropy is increasing? We generally look at states of matter. So what are the three states of matter? Solid, liquid, gas. Which is the most ordered state of matter? Solid. Going to liquid and then going to gas means this is most disordered, right?
Yeah.
And this is the most ordered. Disordered is favored. So any reaction that makes lots and lots of gases is probably 100% going to happen. Any reaction that makes a lot of solids, that's more ordered. We want disorder. We want the disorder, oops, I'm sorry. We want the amount of disorder to go up. So we prefer reactions that make liquids and gases versus those that make solids. And that's just because of we're trying to satisfy the universe. So this is labeled delta S, for this one's labeled delta H. There's a little table we're going to kind of follow through to see which reactions are going to occur spontaneously. What does spontaneous mean? Going to happen without any intervention. It doesn't mean it's going to happen fast. It just means it's going to happen naturally. So you're going to happen without any intervention. Without help. How about that? Because like I said, a catalyst is a helper. It's going to help the reaction happen. We want to just talk about what reactions happen all by themselves without any extra help. So the ways that you figure it out is you have to look at the enthalpy and the entropy. Yeah?
On that last slide, was that it? Blank?
Yeah. Yeah. It's not a complete sentence, but it's there. So whenever things are exothermic, that delta H, is that positive or negative? Negative, okay? When things are getting more disorderly, is entropy increasing or decreasing? Increasing, right. So we said entropy is a measure of disorder. If you increase entropy, you're getting more disorder. You're getting more like a gas, crazy gas particles versus nice little solid. So positive delta S means more disorder. Okay? So if those two things are present, that's a win-win, people. That is a good thing, and the universe means yes, it will happen. It will happen all by itself with no intervention whatsoever. You don't even have to look at it, it's going to happen. So that means like the universe is happy, the universe is double happy, the universe makes this reaction happen. Okay, so opposite, we have delta H, that is endothermic. That's not so great. The universe does not like endothermic reactions. We have a negative delta S, so the disorder is decreasing, so it's getting more what? More ordered. Universe does not like that either, because that's like putting things too close together. They get kind of a lot of potential energy, a lot of stress on the system. So sad, not going to happen. So the reaction does not happen. So this one is yes, always. This one's no, never. The reaction will never happen. Doesn't matter how much you try, it's not going to happen spontaneously. Okay, so negative delta H, endo or exo? Exothermic, right? Negative delta S, more or less disordered?
Less.
Less disordered, so more ordered, okay? So more order. I'm just going to write that there because I'm writing this in different ways so you can see it in all the ways I could ask this of you. If something's exothermic, is that happy or sad? Yeah, we like exothermic reactions. It's releasing pent-up energy. Do we like more order? No, that's too close together. Okay, so then you're like, oh my gosh, what do? I got a happy and a sad here. So this one is,
That's
what? Sometimes? Is that what that is? So sometimes it depends on temperature. Sometimes you got to heat that stuff up and it will happen. If you heat it up enough, or if you cool it down enough, the reaction will happen better. That's a whole nother concept, but I'm just going to put sometimes it depends on temperature. Okay, next one. Endo. Favorite or not? Nope.
Nope.
We do not like endothermic reactions because we want to get rid of the excess energy. Positive entropy. What does that mean?
What's that?
More disorder. Yeah, we like some disorder. So the disorder is increasing here. Okay, so again, tell me what this is. Sometimes it depends on temperature. There you go. Ditto marks there. So what you should be able to do is decide if it's happy, happy, sad, sad, or both. And if it's exothermic and increasing in disorder, yeah, that reaction is totally going to happen. If the reaction is endothermic and decreasing in disorder, nay, never. And then the combination here. So you have a couple examples. We're just going to maybe go through like 3 or 4. On yours, you have this here, right? I want to show you how what we just learned appears in a BCE. So on the BCE, this first one up here, what do you notice this? Do you guys remember what joules are? A unit of energy, right? So if the energy is on the product side, do you think that means it's exothermic or endothermic? Exo, it's exiting, it's being produced, it's going bye-bye. Okay, it's exothermic. So just write delta H, exo, and is that positive or negative?
Negative.
Exothermic is
Negative.
exiting, so it's negative, right. All right, so is that a happy or sad?
Happy.
Right, we like that so far, right?
Yeah.
Okay, then you have to consider the states of matter to determine if it's increasing disorder or decreasing disorder. So let's look. This is balance. This is balance. This one is solid, aqueous, solid. What do we have here? We really don't know. It's going from solid to solid and aqueous, so there's no change. So that one, for the driving forces, I'm sorry, I'm skipping to the next set of questions. This one, I'm telling you, all of them are spontaneous. They're all going to happen. But why? Is it enthalpy that's driving the reaction, or is it entropy that's driving the reaction? Well, since the entropy is not changing, the entropy has nothing to do with whether this reaction is happening or not. Who's controlling it? Enthalpy, right. So the enthalpy, delta H, is controlling that part, making this reaction drive forward. Let's do this one, nacho. This one.
That'd be not
Nacho, actually. Say that wrong. What is this? Tell me my thought process. You say, oh, I see the energy on the reactant side. So what happened? Energy went in. So it's endo. So then you said delta H is positive, and then you said, So obviously enthalpy is not driving this reaction. So let's double check. Is entropy driving this reaction? Yeah, we're going from tight little solid, right? So you got this little thing that's all scrunched together. And then you go liquid. It's an aqueous form, right? So it's kind of moving everywhere. So aqueous is not really liquid, but it's in the side of liquid. Yeah. If it's happy or sad, if it's driving the reaction. So enthalpy is not driving this reaction because it's an endothermic reaction, and the universe does not favor endothermic reactions. Then you looked at your states of matter, and you went from solid to aqueous, and so that delta S is positive or negative? Positive, because it's going up in disorder, and then you're like, yeah, up in disorder is good. So it's the entropy that's driving the reaction. It's delta S. All right, do you feel like that makes sense? If you guys want to do one more of these, let me know which one.
Let's do
Choices.
I don't want to do
Do I need to do
Let's do
another
the
one? The last one. Last one. Which one? This one? Ooh, actually, that's a good one. That one's That one's good. So, tell me your first thought. Okay, so you're like, okay, I'm not going to go through and do my whole jig here. It's exothermic, so favored or not?
Yes.
Favored means happy. Okay, yep, exothermic. You see the the products are the energy, so it's being put out. And then you see how many moles of gas on this side. Oh, it's not balanced. Well, let's balance this first.
Put it 2 in front of it.
Put a 2 in front of this, okay.
Put 2 in front of the A.
Uh-huh.
And 3 in front of the A.
Okay, so now you see gas, 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 right? Well, then you have to go a little further. And 1 second. Oh, thank you. 1. That's a 1. Imaginary 1. Okay, but if you see gas, 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 you're like, I don't know. Then you count moles of gas. If you have maybe 1 mole of gas and then you make 15 moles of gas, that's a big change in disorder. That's a lot more gas, which is a lot more disorder. What do we have here? How many moles of gas are here? 4 moles of gas, and just look at coefficients. So I did 1 plus 3 is 4. This is just 2 moles of gas. So I went from 4 crazy moles of gas to 2. What happened? I lost disorder, right? So what happened? What's delta S? Positive or negative? No, losing disorder. That means disorder goes down. That means it's negative. And is that a good thing or bad thing? No, the universe wants disorder. Universe wants disorder.
Wait, can you explain again how it's not disorder?
So if I have all the same states of matter, I have to have a second tier of reasoning. And so all the same states of matter are here. So my second stage of reasoning is determining the amount of disorder based off the number of moles of that particular type of matter. And all I do is count up the coefficients and add them together. So there's 1 mole of gas of nitrogen and there's 3 moles of hydrogen gas. So total there are 4 moles of gas on the reactant side. That only makes 2 moles of ammonia gas, so 2 moles of gas total. So 4 crazy moles of gas goes down to 2 crazy moles of gas, which is less crazy, which is less disorder. Less disorder, the universe does not like. It wants more disorder. It wants the reaction to release all of its picked up energy. So when you crunch it back down to 2 moles of gas, you're making it more stressed. And so that's why it's a negative sign, and that's why it's not favored. So which of these 2 things are driving the reaction? Enthalpy or entropy? Enthalpy, because that's the favored version. This is the not favored version. Okay, let's do one more. Let's do
The last one.
this one.
Oh.
Predict if it's spontaneous this time. So you know the 2 conditions that must be present for it to be spontaneous. So I'm going to go with this one, lithium chloride, yielding lithium ion, chloride ion, and this stuff. So tell me your thought process, considering enthalpy first. Right, so you see it's exothermic, so delta H is, well, it's negative, and because we want it to be exothermic. Okay, so that's one win.
If it was for a solid,
And aqueous, right? So what's happening to delta S? What'd you say? Well, look, you're going from a solid, which is ordered, to liquid, which is disordered, right? Disorder is good for us, okay? So that's a good, it's increasing in disorder. It's hard because you want to say you're talking about the order part of it, you're actually talking about the disorder part. So you're really focusing on disorder increasing. Yes. And the universe likes disorder. It wants disorder because the reaction itself then has less stress within it. So, both happy? So, is that spontaneous? Yes or no?
Always.
Yes, always. Spontaneous. You don't have to look at it. It's going to happen all by itself. Let's do one more like this. So, now pick your poison. Let's do one of the heat ones.
Plus heat.
The last one. The last one it is. Okay. So, tell me about enthalpy.
Exo.
Okay, so delta H is negative exothermic. Happy, yes, we want it to be exothermic. And then delta S. Let's double check. Tell me your thought process. It's going from solid, yeah, it's balanced. Solid and aqueous to aqueous and gas. Crazy gas, right? Crazy gases are disordered. Crazy gases are disordered.
Positive.
Okay, and okay, so increasing disorder and yeah. So yes, always. These happen to be yes, always. Okay. Shoot. I think we're done here. Yeah.
So that's the one that is, the one above the line.
This one?
NaCl.
Oh, that one. Okay, so exothermic, yeah, and then solid to aqueous, that means increasing disorder, so double yeah. So both of them are driving the reaction. Yep, both of them, yeah.
Go back to the chart thing.
Yep. Fine. My
Are
bad.
these?
There you go.
No, the other, the one that we just did. I think that's one. Or, yeah, that.
Sorry. This is yes, always. Always.
But these equations will ever go from a gas or liquid to a solid?
Yeah. But then that reaction probably wouldn't happen. But it could be written out on paper. You can write anything on paper, it doesn't mean it's going to happen, right? I could write puppy dog plus cat yields cat dog, but it's not going to happen. So, okay, unit review time right now, and I will rotate around for questions, and I want to see problem set 12. Okay, so see problem set 12 on your desk. I will come around with questions. Work on that unit review like a boss. Okay? Do I need to pull up the unit review on the board?
Yes.
Okie dokie. Yes, thank you for waiting.
I texted my grandma to bring my PS12 because I left it at home on the counter. So can I get it to you before the end of the day? Because I have to stay after school anyway.
When I was doing this, I was confused on like how do you determine the needs and the wants, and I looked at a video and it uses like ammonium with the limiting reagents. It just confused me even more.
Hold on. I'm trying to pull up the unit review, and then I'll go through your question. I don't know where I put the unit review.
Wait, only the purple one?
I would even ask that kind of question.
Sorry.
It's not your fault.
I was thinking I could think
I can't find it. We're just stealing good vegetables.
Hey, take a couple of Starburst.
Sorry, Caroline.
Oh, you just hit my brain.
I didn't know.